I haven't met most of you, but yeah, so I'm studying computer science and computer graphics that has been doing a lot of work on sound synthesis, physics-based sound synthesis, which I think you know a lot about. But it's from a different perspective than computer graphics, where a land where people are like, why do you do sound, and what are you doing sound here for? This is graphics, this is not graphics. So I feel like at least there's some people that can appreciate why you would want to simulate sound. Okay, so this is a bunch of work that's been done by a number of Ph.D. students primarily at Cornell University and some other collaborators. And so we had an NSF grant as well as Intel funding to do physics-based sound. And the primary goal was to do this for the perspective of computer animation and interactive virtual environments in the future. So here's a high-level comment from the National Academy of Engineering talking about why feedback is important in the future. So they listed as one of their grand challenges to provide interactive multimodal feedback. So I'm really interested in where this can go with VR in the future, especially ones that are based on physics-based models. Another motivation for why we want to do sound is just all the work in physics-based animation. So here's a gratuitous animation of all kinds of destruction and physics-based models of rigid bodies, fracture, turbulence, different things like this from one of the projects that we did. Not this movie, but just a simulation technology. And so it's really at the point now in the last 10, 20 years where you can simulate all kinds of physics, but all of these things have great music to them. So they don't really consider sound. Another important motivation is just where we've gotten to in parallel computing. So if you think about like GPU computing, GPUs are like the parallel, the killer app for parallel computing. So graphics is a killer app that basically made parallel computing a commodity in realisms. Everybody's got a parallel GPU in their pocket. It's because GPUs in games put it there. But we can also use this for sound. But all of this stuff sort of suggests that we get all the physics and we have all the parallel compute. We should just be able to have great interactive virtual experiences. But the reality is that it's always an afterthought, sound, for these applications. Sound is done in post-production. Sound is done by calling some appropriate sound clip. And it's not really an integrated experience. And so the way I sell it is basically what's happened in computer animation and physics-based animation in particular is basically a repeat of what we saw 100 years ago, where sound was basically not included. It came after the fact. And you can always use add it after, right? And that's really the way that it's been treated. Somebody in post-production will fix it, and we just move on. And now as things become faster and more automated, then I think that we want to get beyond this notion that you can just always add sound after the fact and actually compute it as an integrated quantity that's treated as a first-class citizen in virtual content production. So in order to do this, there's a lot of steps that you have to do. One is you need to simulate things with more fidelity than you would just to make a picture. Because there's a lot of stuff between the frames which is missing that you don't have to compute if you just want to make a visual medium. And so what we want to do is be able to take any phenomenon, say it's like some thin shell object or something. We want to figure out how it vibrates or what the acoustic properties are. And then we want to be able to synthesize some radiation or transfer of some sort of medium of vibration to the listener. And then there's a listening experience which can be modeled in sort of ways that people have studied fairly extensively. So when we started out in this project, our goal was to basically address different sound phenomena that were done in animation and all the kind of things that we need to do to make stuff go on the screen. Sorry, I just bite here in a rainstorm, so I'm slightly out of breath. But anyway, so we looked at different phenomena, solid bodies, water, destruction, so on, and different types of algorithms to make it fast. So it's like we know that you can just literally discretize everything and time step it all. The problem has a solution, we can do that, but that's not a practical way to do anything. We want it to be a little bit more expensive than just animating things in the first place. We don't want it to be a huge amount of extra work. So we need fast methods to do this, precomputation, reduced order modeling, and different things like that, which was our main focus. And there's a lot of problems with this. And often when I talk to people, they kind of think that you're crazy, you know, nobody's ever going to do that. It's just so much work, you know. And I always joke with them, because they're usually graphics people, and I say, well, you know, if you think about how much work it would be to render a picture of the world, you know, you'd have to model the whole world and take like thousands of triangles. You'd have to figure out the color of every triangle. You'd have to like transport rays between everything. You need like a bloody supercomputer, right? But it seemed ridiculous, you know, decades ago, but now it's just, you know, mainstream. So I think a lot of these problems will just be solved if we actually make progress and show people what they're missing. So that's where we started. Here's some of the projects that I'm going to talk about, sort of in many ways the first different things. So one of the sort of, you know, important special cases is rigid bodies, so-called rigid bodies, which is a silly name because they're not. And so the way we simulate them is with modal vibration models, which are standard, you know, things in engineering work since the, you know, half a century ago. And so basically we take a solid body, we mesh it, we simulate the equations of motion for small deformations, compute eigenmodes, and then for each of those eigenmodes they have different frequencies, which people are, I'm sure, familiar with. And so then whenever we have impulses in a rigid body simulator, we can apply those to the body and get some sort of basic excitation. And the details about how to do that to make it sound good are interesting, but I'm not going to talk about them right now. And then, since we don't hear the eigenmode vibrations directly, we have to figure out what the sound field is around it. So for a harmonic vibration of the solid, we can figure out a transfer function, just an amplitude model for it based on solving the frequency domain wave equation. So we do that with like a fast Helmholtz boundary element solver. And we can get that field, encode it in some multiple expansion or in a texture map or any number of different ways. And that gives us a simple way to basically display the sound as some sort of eigenvibration weighted by these transfer functions, which we encode in some way I can talk about later. And mathematically, there's just a generalized eigenvalue problem we solve, and then each of the eigenmodes is a simple harmonic oscillator that we time step in different ways, depending on whether or not the coefficients change. If they're fixed, you can use an infinite impulse response filter. If not, you time step them however. And then we solve this ahead of time. So the key thing is that this decomposition and these solves are all done ahead of time. So at runtime, you have very cheap evaluations that can run in real time. So you can simulate thousands of modes in real time. So the sound rendering model can be better if you have a better listening experience. But that's basically the simplest model. And so here's an example of what that simple model gives you. So this is just no ground reflections, just a single object in outer space. So a lot of techniques I'm going to show you are these sort of prototypical kind of Phong shading equivalents where we just have a single object with nothing else and linear superposition of these models. And really putting everything together, integrating and coupling everything is future work.
So in that case, every touch of the plate generates a new set of new forcing function with eigenmodes?
Yeah, so basically, in the body's frame of reference, you're moving around as the object tumbles around, and we evaluate the sound there. Every impulse is applied, so it gets applied, and the ODE for every mode just integrates those impulses as they come. And they may be like distributed in time based on some Hertz contact model or some sort of time scale. But yeah, everything is pre-computed, the model's made, and then it just time step these things.
But as it's rolling on its edge, each time step is another impulse because it's falling on the edge.
Yeah, so in this case, we probably time stepped it at on the order of like a kilohertz rate, and then every time we got an impulse, we would apply that to the body in some smooth way if it was a high frequency rate. Yeah, so a lot of these slides are like just videos, so please just ask questions if you have that. Another important effect to get is the directionality that the wave equation has. Often this is ignored because for various simplifications. So if you just model the sound as a point source, you get something like this. So you get a bit of fall off. It gets a little louder when it's closer, but you don't get directionality effects, which is a really important effect. So here's with directionality from the wave equation. And aside from directionality, another really big reason to do transfer solves for the Helmholtz equation for modal models is that they really affect the radiation efficiency and amplitude of relative modes. So some modes may be completely quiet, like a wine glass has a twist mode, which has basically no normal velocity. And so it's basically completely quiet. And if you don't include that, then you just are rendering things that can't be heard. One project we had was just to bake transfer. I call this transfer. Different people call it like transfer functions or Z transforms of things. I'm calling transfer just like these time-independent amplitude maps of the acoustic field for any individual mode. And so we looked at ways to basically map these things for constant time evaluation instead of like if you have a multiple expansion, to evaluate a field at one point you have to sum up a bunch of things, which is a speed time trade-off. In this case, we had a project that looked at putting in all the texture maps and then evaluating some expansion which converged in a constant number of terms. And so we got all these different fields, and there's a lot of data. Not all of it you can hear, so there's perceptual encoding is not considered in this case. But we could evaluate the transfer for each of the modes in basically constant operation. One other thing we looked at was how to compress the actual eigenmodes themselves. So the modal synthesis approaches for finite element models works really well, but one downside is that you actually have to store the model. And if you actually have these eigenmodes stored, then if you have R modes, say like on the order of hundreds, or maybe big objects, it could get up to thousands that you could hear. And then we have the number of surface degrees of freedom that you have to store. And the main reason that you have to store this stuff is that at runtime, whenever you have an impulse applied at some contact point for non-penetration or friction, then you have to map that impulse in the modal subspace. So for this vertex, you basically look up some modes at that vertex, and then these are some 3 vectors here, and then you project that 3-vector force into the modal subspace with a dot product. And so you have to keep those values around at runtime so that you can actually figure out what the excitation is. And it's really just a dense matrix, it's no big deal, but it can be a lot of data in some cases. So here's an example. So this is a smallish backhoe bucket, and it only has 100,000 vertices, but it takes up about 575 megs as floats, which is, like, if you're interested in high quality sound, then maybe that's okay, but if you're not, or if you're willing to tolerate it, then it's a problem. And basically there's just, the bigger objects get, the more modes they have. And so there's all these shapes that are there. We only store the surface degrees of freedom. But they get more and more diseased looking at higher frequencies. And you get, there's a lot of data. So it's just life, but it's not great if you have more than one object, or maybe you have thousands of objects, or you want to encode an entire virtual world, right? So this is a bit of a problem. So one thing that we looked at was, a lot of the modes are smooth. Initially say, oh, these modes are sines and cosines, or there's some simple shapes, right? They're not really simple shapes for general objects, but they are smooth in many cases. So we looked at how to use a smooth interpolation scheme. We use moving least squares, which basically has a bunch of control points and vectors you can fit to the data. And if you use few points, then you can do a good job of getting some compression. And it turns out you can do this really well. I'm not going to go into the details, but we have an optimization approach that does that. Another way that we got compression is just for man-made objects that have symmetry, such as a bowl. Here's a compression mode of a bowl. Here's another mode. These both have basically degenerate eigenvalues, have the same frequency of vibration, and so they're rotations of each other. So basically you can encode the intermode symmetry to get a factor of 2 compression on these pair modes. And then you can also exploit the intramode symmetry, that this mode is basically replicated versions of itself. And as you get to higher and higher modes, these cylindrical symmetric cases show up. So we did this where we basically encoded little patches and figured out how to map them between modes. One problem that comes up though is that, of course, as you get to higher frequencies, you get more wiggles. So your ability to compress all this stuff kind of goes downhill at these higher frequencies. And in this case, mode 48 here has got a bunch of wiggles. But if it was a bigger object, the higher modes would have increasing complexity, as you saw for the backhoe bucket. So in this case, the thing that comes to save you is just your hearing. It's pretty lousy at high frequencies. So here's your frequency you're most sensitive at. And as you get to these higher frequencies where the modes are really complicated, you can't really hear very well. At some point, we just throw them all away, right? So the conundrum is that these modes are very important, we must keep them all, and then at some point you say, I don't care anymore. And at the moment when you don't care anymore is when they're most complicated. So there's kind of it doesn't make any sense, right? So you can exploit that by encoding higher levels of air at the higher frequencies. And we came up with a way to do that, which I won't go into the details on. But basically what happens is the number of control points we have is some nominal number, and then we encode different amounts of detail. And as we get to the highest frequencies, we stop encoding more detail because you can't really even hear the air. And this helps, especially for big objects. So for the backhoe, here in this case it had about 575 megs, single precision, goes down to 10 megs. And you can hear a bit of a difference, but you can keep it much lower for a similar level of error. If the objects are symmetric, cylindrically symmetric, in this case you get massive savings because there's not really much going on. This one has no symmetries, but you can still get significant compression rates.
Excuse me, do you make any frequency extrapolation so that you would guess what will be in the high frequencies based on what you got in the low end?
I'm not entirely sure what you mean.
So now you compute accurately the low end frequencies. So have you considered extrapolating to the high end?
No. So what we do is we do like some modal analysis and radiation analysis of all the modes.
Yeah.
And then that's expensive, but we do that ahead of time, and then we compress them all individually based on human hearing sensitivity.
Okay.
Yeah. So it's not really optimized in the sense that we actually have to analyze and compute everything. Ideally, we'd like to not compute it if we know it's not important, but we didn't do that. Yeah. The problem really is that you don't know where the object's going to be hit or where you're going to listen to it. So there's always a worst case scenario where you could hit it with a case where it's loudest at this particular list. And so you can't really throw everything away. So we can't bound the error in any individual excitation and listening location. We just do it an average in a power-based way. So it's not really ideally satisfying that way. But anyway, so here's an example. So before and after this compression. Oops. Okay, just hitting it at different locations here. So anyway, the point is that they're very similar. Yeah.
So there's definitely a difference between the two, but I'd be hard pressed to say which one is the right one.
That's true. Yeah. So if you're just interested in plausibility, you probably have your error rate is probably way too low. Yeah. We just wanted to show that we could still get reasonable compression even with basically the same. We have like hours of this riveting footage on our website. A few more to go.
Have you done the perceptual test? I mean, at some point, can experts tell which one's real and which one's...
There are cases where you can hear for specific vertices, specific positions, you can hear the difference.
I mean, I've heard a difference, but I couldn't tell you which one is right.
Yeah, I can't tell it. Yeah, just a blind test, you can't tell which one's right. So anyway, so this is was motivated by just the amount of data that we had. It wasn't necessarily the most exciting project we did, but it was. I think it's really important to look at compression for a lot of these models, since there is a lot of data. So another project we looked at was related to basically rigid body models, but in particular ones that can break. So this is really important for computer animation graphics where people are basically highly destructive physics people. Smash cities and everything all the time. So if you just have an object and it breaks, then what do you do? And so we looked at brittle fracture, which is really important for sound. And for modal models, you can use them for rigid bodies, and then when they break, we wanted to basically use them for the pieces. And this is a preview of our result. This is sort of an intermediate result because we have results later that are better in different ways I'll talk about. So the basic idea is that you start off with a single object, you pre-compute a modal model, but the problem is that as you undergo fracture, you basically generate tons of modal models. So you throw away the models that you spent all this time making, so you can't get much reuse, and you generate more. So this is like a worst case scenario because you just have a tree of models you have to analyze, which is really unfortunate. We did a bunch of experiments where we dropped objects in very careful ways so they would bounce and not break, and then bounce the second time and break. And in this case, you can basically see a certain spectrum of the original model, and then when it breaks into two similar pieces, it was scored. They have some different base frequencies which are higher, but there's essentially the dominant content of the sound is this modal spectra. There's not like some other giant crack sound here. It's actually relatively quiet, you could argue. And then it's basically the pieces which are making the sound. So we use this to motivate the idea of having these modal sound models. And here's sort of a qualitatively similar result from our simulated case. When we're doing the rigid body simulation, what we do is we look at the impulses applied and then do some sort of very simple static stress analysis of the bodies. And there's some details about how we do this, but basically at some high temporal rates when we're simulating the bodies crashing around, for any impulse applied F, we basically figure out what sort of stress that would do. And if it's too much stress, it can break. And if it breaks, we break it into some pieces in some procedural way. The details are not important. It could be done more or less accurately, but it's not really critical to the sound model. The one thing that's important is that we don't break it into too many pieces, so there's some sort of notion of energy that things are conserved. So we can figure out the displacement and figure out the stress associated with that, and we have a sparse solver to do this. One property that we want to capture is the dependence on fracture toughness. So the objects that are weaker tend to have more pieces, and objects that are tougher don't tend to break as much. So basically, if you have like a glass sphere, you drop it, it breaks in two. The amount of area you expose should be related to the amount of energy that was absorbed by the fracture, because you're basically splitting the material and exposing new area which requires energy. And so here's some results. So we're able to simulate these models for a wide range of frequencies. And every time we create a new body, we analyze its vibrations and radiation and just turn the crank and do this in parallel. So this one turned out to be really, really loud, and a lot of objects at the end you can't hear because there's not any compression of the dynamic range.
So have you constructed several real-life ground truth scenarios to compare with?
No, I haven't. No. I don't think it's that close, actually.
So can you do that in real time, or?
No.
No, you can't. Yeah. Right.
Let me get to that. Okay, so the last example, the table, took about 18,000 minutes to compute that.
What's that in days?
What's that?
What is that in days?
Yeah, well, it's, I don't know, a day. So basically the bottleneck is just as you'd expect, all the modal analysis and all the radiation analysis. This can be done in parallel, so it actually just ran on our cluster. The main bottleneck in all of our wall clock time was always just the time stepping the rigid body fracture simulation, which was not very parallel. So the nice thing about sound is that even though this is a lot of time serial, if you do it in parallel on like hundreds of processors like we did, it doesn't actually take that long. It's only, it took 40 minutes, whereas the rigid body simulation took an hour or something, even because it was serial. So, but still, it's arguably too long to spend for a 5-second clip. So we wanted to look at ways to speed this up. And the main problem is just model generation. Every time we smash it, we generate tons of models and have to analyze all their vibrations. And is this really necessary? So one thing we looked at was just, if we have all these pieces of debris that are thrown on the ground, then can we really hear the difference between their sound models and the same forces and impulses applied to, say, these sound models? You know, they have similar frequency distribution. Can you hear the difference? And we did various comparisons and we couldn't. So we thought this would be a good idea to exploit. And so basically, whenever we have an impulse applied to some piece of debris, we classify it in terms of its shape distribution. It's just an ellipsoid. And then we apply the impulse to this body in some sort of tabulated canonical. And the one thing that's important is the base frequency of a model. So we actually solve for the base frequency of the debris, one frequency only though, and then we use that to match it, scale our other model so it has a similar base frequency. There's details about how we scale things. And we basically tabulate this little lookup table between spheres, pancakes, and scars. And then whenever we have a new body, we just map it into there, find the nearest neighbor, and play that models. So here, for big objects, you can tell the difference. Like here's a plate. I'm not sure why this video didn't play. So it's clearly not an ellipsoid. There's much more interesting spectral frequency variations, but it gives you the rough sound. Yeah.
So you let one ellipsoid stand as a proxy for that entire plate?
For the sound model, the collision detection and physical forces are still related to the original shape. It's just the actual sound model. Yeah. It's moving around there. So in that case, you can hear a difference, but when you have a lot of debris and a lot of tiny things, you're really not able to hear the difference. So judge for yourself though. So above is the direct evaluation that has all the original modes. And then as we go down, progressively more and more of the smaller and increasingly larger objects are entirely replaced by these ellipsoid models. And some fraction of modes that are replaced in total. So how many people could hear a difference? Here's some. There's a little bit of difference. It's not like, the question is it worth 18,000 minutes or is it worth 36 minutes? This is almost entirely disk I/O to load in the simulation data, so it's not optimized, but you could imagine a sound engine that was entirely based on just ellipsoids or something. Maybe people couldn't tell. I mean, I don't recommend simulating like a violin as an ellipsoid, but maybe a piece of broken glass, it's okay. Another thing we looked at was basically how to get better contact forces. So all of these, there's a lot of work on animating rigid body sound models in graphics and VR, and they all use basically rigid bodies to generate forces that are then applied to these modal vibration models. So this is really fast to do this, but the problem is that there's some, it doesn't really entirely make sense. On one hand, you're saying they're vibrating models, on the other hand, you're saying they're perfectly rigid models. So there's cases where you can see it doesn't necessarily make sense. And here's an example. If you just have a table, if everything is simulated as rigid bodies, then when you hit the table, nothing should happen. Because everything's rigid, it's on the ground, it's a rigid body. But if you bang on the table really loudly, then you'll make other objects move. And so what we did was we looked at, okay, let's just compute all the contact forces and couple all the modes together so that we actually get all these small vibrations to couple together. And when you do that, then obviously you can get these extra effects. The problem is that it's actually quite expensive. If you actually want to simulate all of these bodies as fully deformable models and time-step at their audio rates, compute contact forces and frictional impulses accurately, you can do this, and it takes forever. Like if we did this previous example with a traditional multi-body dynamics code, running at audio rates, computing frictional impulses with some nice quadratic programming solver, it took like literally on the order of like months. And you could do it, but it's just not really, nobody's going to wait that long. And just at a high level, what's happening is that you have a lot of modal degrees of freedom, hundreds of modes, or thousands of modes, and they're all coupled together by this F equals ma, where the forces are related to the number of contacts for the normal forces, and then there's the frictional disk of forces that have to be computed. And basically, the number of modes you have is a problem. There's lots of them, they're all coupled together, so it's all dense, coupled at audio rates. And you have all these frictional forces you have to solve for in normal forces. And so one way that we spent quite a while on this, but one thing you could do is basically reduce the number of contacts you have so that it's as few as possible, and then throw away as many modes as you can. The thing is, when the objects are on the ground and at rest, not making any sound, you can throw them all away. You don't have to simulate them. But also the high frequencies decay really quickly, so you can throw them away after maybe tens of milliseconds. So this helps a lot. And then we also, once we have, when we have lower and lower frequencies, because we've thrown away high frequency modes, we can take bigger time steps. So basically our strategy is to throw away as many contacts as we can, but still visual, same motion, throw away as many modes as we can, and time step everything coarser and coarser and coarser. And that's basically what we did. And there's a lot of details on contact solves, which I would not talk anything about. Here's a picture though, a ruler getting excited by an impulse. Since I encourage my students to do this in class. And if you have all the degrees of freedom, it's red, and if it goes down to blue, then you throw them away. So here's like all the modes, and then once it gets excited by contact forces, and it aggressively throws them away when they're not needed anymore. And then we take these forces and then use them to drive a sound model in a second pass. It's running alongside it. There's the result. So at the end of the day, you can get big speed ups in big systems. So in a case like this, we never would have been able to do this example previously, but it has something on the order of like 4 million solves of all these things coupled together. It ran overnight. Which is see if we could make an animation that had all the sound computed with all the forces evaluated and coupled. One thing that happened as soon as we made this is we realized we made a big mistake because all of the balls had no sound. And we were like, why? Oh, why would they have sound? Because all of these marbles had like, their lowest frequency was something like 45 kilohertz or something. So all of the marbles were entirely silent. They, of course, excited the other objects, but they had no clicking sound at all. And so we were like, oh yeah, because all the modal sound models we did were big objects. But the tiny objects don't produce any interesting vibrations. This led to another project, which was on acceleration noise. And so the typical scenario in a lot of cases, you have some big resonator, like this table, and all these little objects hitting it, but you basically only get the sound of the big object with modal sound. And so it kind of has some sound, but it's not very crisp, because all of the little pieces are missing. And so essentially, we're trying to simulate the sound waves coming off the object, and the boundary condition on the solid is basically an acceleration boundary condition. And usually we model this just coming from the modal vibration, the vibration of the ringing of the surface. But in reality, there's another huge source of acceleration due to the rigid impact. Like within like tens of microseconds, the rigid body, if it's really rigid, churns around. And that's the missing impulse. And so here's an example from this paper in 1978 that's showing two hammers being lifted up and then dropped down. Very painful room to be in, I'm sure. It's pretty loud sound pressure of newtons per meter squared. This is a big spike. And this is essentially the acceleration noise of the rigid component. And then there's ringing noise from the hammers. And so basically we're missing this click. which is, causes hearing loss, but also causes sounds to be very crisp. So this is a previous model with just modal sound at a table model, and then this is the missing sound and then together. And so that's the approach that we did. So for really tiny objects, you can treat them as acoustically compact and basically come up with a simpler model. But for general shapes, it's a little bit, you need to compute the sound using the wave equation. I'll talk about after I show these results. So basically what we do is I don't want to have time to talk about it all, but we basically look at like the 6 dimensions of translational and angular acceleration and pre-compute little impulse responses of the body to get the outgoing sound field. And that's what we use. One problem is that every time you have a new object, like in fracture, you have a new radiation model. So we looked at, again, a sound bank approach for little debris. And then we compress this outgoing sound field for each of these. And there's a convolution with this impulse response to get the sound, which I'm sure you can imagine. So we're able to do lots of bodies using this extension. And so in each of these cases, I'm showing you basically an ellipsoid modal sound model with an ellipsoid acceleration noise model, so for the click. And it sounds a little crisper than if you just had the modal model. Or in some cases, there's actually sound instead of no sound. For fracture, it's actually really useful, because previously when we did the fracture, we didn't have any acceleration noise for the tiny pieces. So a lot of them were basically just hitting a ground resonator model, or they were, maybe they were quiet or just had a few modes, but they didn't have the kind of crispness that we see here. This is actually my favorite result. Play it again. I guess it's only a mother would love, or only I would love this broken plate debris. It's my favorite result. It's my life achievement, is broken plates. Okay. Okay, so another project that we worked on was vibrating shells. So it really applies to any type of rigid modal solid where it starts to deform enough that it can couple the modes together. And so these larger deformations can cause nonlinearities, which are well known in music for all kinds of instruments. So, of course, I'm not interested in instruments so much as I am in garbage and broken debris, but in computer animation. But so once these objects bend, the bending couples together the modes because of the strong stretch and shear resistance in shells. And so it makes it nonlinear. And so we looked at how to simulate these shells, which people have looked at this a lot in computer music, I know, but we wanted to do this for animation and get large time steps for general shapes. So here's a kind of result that we got. And so the key thing for the sound is that when you excite a linear model, then the modes just ring, but you don't get any coupling. Whereas the nonlinear model, when the modes are coupled, then you get this coupling. So this is well known, and it's expensive to compute from first principles. And so what we wanted to do is find a really cheap alternative that was still physically based on any geometry that someone would generate. And so the thing that we looked at was a thing called reduced-order remodeling, which is something that we've been doing in our group for a while. Basically, we have the equations of motion, mass matrix times acceleration plus internal forces due to the deformable body, and then some external contact forces. And so we can discretize the system and get these equations and solve them, but it's slow. So what we do is we take just the linear modes of the body, because we're only looking at very small deformations. So it's not geometric nonlinearity that we want. So we're happy with the linear modes, but we want to project the full equations of motion into the subspace. And so you can normalize things, so that goes away. You end up with a system of ODEs for each of the modes, but now instead of this being like a diagonal decoupled system of simple harmonic oscillators, like for linear modal analysis, you end up with some force model that couples all the modes together. That makes it really slow, and it's not going to be fast. So what we want to do then is not have to evaluate all the degrees of freedom of the finite element model to figure out this, but to do something cheaper. And so linear modal analysis, all the modes are decoupled. So the force on the first mode is only dependent on the first mode's coordinate Q1, and they're all diagonalized. And in other cases, they're like certain polynomials, which doesn't scale well to large numbers of mode R. But so what we did is for shells and in other types of solids is basically it's basically like some convex optimization approach where you basically find some sparse set of features which you can evaluate that still allow you to approximate the full energy of the system. And that allows you to just take the modal coordinate and only evaluate the sparse set instead of all the elements, and then go and evaluate the force using something that's only quadratic in the subspace. So if you have like order 100 modes, then you have order 10,000 operations to compute the force. And so basically you can think of it as like a sum where you have the energy, the force is a gradient of the energy, which is an integral over space. And then we only evaluate basically a set of magic weights for a set of magic integration points, so that we take the full model and only evaluate a sparse set of points to get the force response. And so you can have like on the order of 100 modes and then on the order of a millisecond evaluate the response, so you can time step it quickly. That's the basic idea. So here's the trash can. We only evaluate these points on the body in order to get the force response. And more recent approaches can use fewer points, but the key idea is that you don't evaluate everything. So here's an example. So this is a least squares error fit for the force model. And here's the unreduced model time step. It only has 43,000 degrees of freedom. Sounds like that. And here's a fit. It has 11% error. So it doesn't quite have the same basiness in this particular case. It's all just uniformly fit, doesn't care about frequencies. This one took 19 days to compute, just using explicit numeric time step the shell model at audio rates, or you have to go higher. And it's just, you can do it, but it's expensive. And this one only took like 3 hours on a laptop. Actually, this was on a 16-core workstation, I should say, running parallel. So this allows us to make animations with static. Here's a comparison just to show the effect. So I'm going to show you the case with the nonlinear model that we have, the reduced order model, and then just the linear transfer model for each mode, as well as the linear modal model, and then a model that's people using graphics, which is just to not do transfer for the radiation at all, just to use like a 1/r model with some effective motion for the surface to give you the amplitude. So I should just say the last model is really fast, so it runs in real time. Typically, some people say I may try to make it look bad, but we actually use the same material parameters for all the models. And so typically, if you're going to use this model, you want to tune them to non-physical values to make it sound a little better. But you can hear the effect of the chaotic vibrations. We also looked at other types of shells. We looked at cloth models. I don't know how much time do you have time? Yeah, I'm not going to go over this, but basically cloth is hard, and we had to use a lot of data to basically drive data models with the cloth simulation, because we couldn't simulate the sound from first principles.
So this is mostly friction-based then?
It's pretty cheap. You could do it in real time, but there's a graph search, energy minimization step that's expensive. I'm just going to skip this. So one of the things, how am I doing on time? How much time do I have on my?
It's pretty up to you, but I'd say, 15,
Okay.
20 minutes.
Okay.
Yeah. So,
Okay. Yeah, so other things that we looked at were water. So this is actually a project we've been looking at for a long time and still looking at. So basically, yeah, when I moved to Ithaca, one of the things that was really obvious was that I was always at these gorges, these waterfalls, and there's all this sound. And I started thinking, why the heck does water make sound? And it'd be cool if we could simulate, animate water with sound from first principles. And unfortunately, I didn't appreciate how much time this was going to take up over the next so many years of my life. But one of the exciting things is that bubbles are basically the source of all the sound. In fact, it's really hard, and it's been known for a long time that it's very hard for water to make much noise at all unless it has bubbles entrained in it. And there's actually a great book by Tom Layton on the acoustic bubbles and the properties they have. So it turned out to be really important in oceanography and all kinds of different fields. So this paper we looked at, this is a work we did that looked at trying to animate water with sounds. And it's a very simplistic approach in retrospect, and it's not predictive, but we tried to do something. So basically what we did was we simulated water using just a single phase simulation, which didn't include any air at all. And then we entrained bubbles in some randomized way, which is common in graphics. And then we figured out how these vibrated and move around in the fluid. And then the main step from the acoustics point of view is figuring out how the surface of the fluid vibrates. So the bubbles vibrate very strongly because of surface tension, cause the fluid surface to vibrate. And then we can figure out how that causes it to radiate, basically like a shape-changing loudspeaker. At very slow rates, the fluid is moving, it's animating, splashing around, but it's vibrating rapidly because of these bubbles. And that's the source of the sound, not the actual visual splatter or anything. That doesn't really do anything. And then finally, we render the sound at the listening location. Here's a preview. Okay, so the basic model for all these bubbles in most of the sound is basically just a simple harmonic oscillator. So each bubble essentially has some damping due to various factors that you can look up in a book. And the frequency is determined by its size, so that's not at all the end of the story, but that's the model we use. And then the forcing is due to entrainment, which is due to increased pressure due to surface tension, so-called class pressure. This is a model people use. It's actually completely wrong, and it's actually people don't understand how the forces are driven. That's the short end of the story, but that's what we did. And then here's the vibration of each bubble, and then you still need to know how loud it is. So we have a model of the mapping of bubble amplitude to the amplitude of your ear, which we have to estimate. This is our transfer function. It's just a function of space. And it slowly varies in time as the fluid and bubbles move. So this is basically what we do. It's a very parallel model of the sound, and we have to estimate the amplitude P for each bubble. I'm going to probably skip over how we do the details of this just for time, but basically over time each of the bubbles have different frequencies. Blue ones are low frequencies and red is high frequency. And the amplitude varies over on the order of 100-fold variation, which you can hear. And if you ignore that, then it just sounds like noise. Basically, we estimate a Green's function for the bubble. We put a point source inside the fluid where the bubble is, and we solve a dual domain problem where we have one sound speed in the water and one in the air. We figure out how the air moves, how the fluid surface moves first. This is the first step. And then we use that to figure out how the sound field outside goes, like we did for modal models. And we have to do this for like on the order of hundreds of thousands of solves. So we do something really, really cheap using some equivalent source approximation, which I'm just going to skip over. But basically, we estimate a few coefficients for the interior problem, figure out the surface moves, and then we solve the least squares problem. And then we can figure out how to do this for the air too. But basically, at the end of the day, we know how the surface moves for each bubble, and we have a model of how the sound pressure is varying around the fluid body. We don't evaluate the sound waves, but here's a picture just to show you what the model actually thinks is happening. It's some very slowed down speed. And so here to show you without the transfer and with transfer. So if you just listen to the sinusoid, damn sinusoids basically for each bubble, this is what you get, and with the transfer it has more variation. So there's more amplitude variation due to the geometry. So since this I'm going to skip this last result because this basically saw it before. Yeah, in reality it's much more complicated, right? Here's more recently we've been working on this, and I'll show you this result. Since then we basically looked at how to simulate full two-phase air and liquid simulations at really small sub-millimeter scales, and with more accurate surface tension models. And then from first principles can predict the sound more without randomized bubbles or some better forcing models. And these are the results that come out of the simulator that we have now. They're still approximate, but they're getting better. I will not tell you anything about how we did that. We did another project. This is like all these projects, and then we did this, and then we did this. We did a project on fire, which is important in graphics. Basically, the rate of change of heat release rate in the fire is what we used as a sound source model. Which is about the simplest model that we could use and still estimate from graphics applications. So basically this source became it's basically like a monopole source for some smallish fire, like a candle. And so we just basically have to figure out the rate of change of this heat release rate to basically get fluctuations in the fire. The problem is that if you look at real fire, here's an animation of my wife shaking around some burning thing in the garage dangerously. Then there's all this detail that it's very hard to actually simulate, especially in a graphic simulation. They don't even know what the chemistry is, or let alone they're not willing to time step at the detail they need to resolve features. So they can't simulate fire from their animations. But they want to. So the question is, how do you get these higher frequencies if you don't have anything in your animation beyond like a couple hundred hertz? So that's the problem, is how to simulate it without simulating it. So what we did was we basically came up with a low frequency model. So given the animation, we would basically estimate an isosurface for the flame front. And then if we have a premixed fuel assumption, then where it's premixed with air, the fuel, then it basically, as it flows through the flame front, it's going to burn. And so the rate at which the fuel flows through the flame front, this flux, gives us an estimate of the heat release rate. And so what we're going to do then is use the rate of change of how quickly it flows through the flame front, integrated over the surface, as a model for the heat release rate. And that's basically what we did. And so we can estimate this simple flux, velocity flux for the flame front, from an animation package, like Houdini or something, and then take the derivative of some suitably upsampled some signal. And that would give us a sound model that we could use. And here's what we get for that animation. So it's synchronized, which is about all you can say. And it's, I mean, it's clearly band limited. So what we did then is basically look at how to synthesize high frequency detail. We took real sounds and took them and then built a class pyramid out of these, progressively smoothing and coarsening them. And then we used this to build basically a set of features so we could map how some structure at the coarse scale mapped to the next scale. We built like a database and did nearest neighbor lookup. And then given a simulation sound, then we could progressively add more and more detail to it to add all this extra sort of correlated features. And you could use various types of fire sounds that you wanted and then synthesize detail to match your simulation.
So you're essentially doing extrapolation in the space domain.
No, this is all in the audio domain. So we synthesize the sound just from the simulation. It's band limited, and then we take that low frequency signal and upsample it using
In
data.
the time domain.
Yeah,
Okay.
yeah. So sound texture synthesis basically.
Because people do sound extrapolation for extending the high frequency of sounds.
Yeah. So we did two
Bandwidth
things.
extrapolation, yeah.
We did bandwidth extension, but then the problem, I didn't talk about that, but I have results for that on the webpage. And the problem with that is that you could use a power law for the sound model. It works really good if you have, like, for audio, if you want to get cymbal craft or something where you already have a lot of frequency. But the problem is that we have like no signal, right? Like 300 hertz, and we can't just like use a power law for everything after that because everything sounds the same then. It all sounds like, you blow on a candle or you set off a bomb, it all sounds like, so those didn't work as well as real data, unfortunately, for ours. So anyway, so that's how we made some sound for simulations that otherwise didn't have anything going for them. So yeah, so I joke that if you want to simulate anything, you have to model it accurately and get the sound out. So if you wanted to simulate a ball of garlic, it might take a couple PhDs, but you could figure out how all these impacts, how this garlic shell crushes and rubs against the neighboring one, and how it's actually not a single rigid body, there's multiple parts, there's fracture, they can be torn apart. So like the physically based approach could be taken too far, and so, could you tell the sound between organic or non-organic garlic? It's slightly old. Anyway, so, so how would you simulate garlic sounds with a physics-based model? So one of the things we looked at was how to use different types of data in our simulations, and one playful thing that we looked at was how instead of trying to do a forward synthesis problem where you took the animation, and then synthesized sound from it using physics-based models, could you actually synchronize the sounds by taking the sound and then searching for motions that were synchronized with them, which seems kind of crazy, but we actually did this for rigid body animations, and it's a project we call inverse Foley animation, to synchronize rigid body motions to sounds. So basically what we did can be summarized with this picture of the sound down here. So here's a sound of a wrench falling on a table. We have a suitable proxy wrench here, 3D model, but this sound actually has a bunch of discrete events at impact times. And what we did is we basically figure out what these times are by hand or automatically, and then we also record the amplitude, get the amplitude of these events. And then we also classify periods where there's some continuous sound, like some rolling or sliding, and different types of continuous events which aren't very discrete. And then so given these times and amplitudes, then we basically we search the space of all possible rigid body motions for this body to find the motions which have these times and amplitudes. It seems crazy, but there's a way to do it, and it is crazy, I swear. But you can actually do this. And so here are animations that were automatically generated for these different sounds. Okay, so that's how we did the garlic sound. There was this one example with the Lego where sometimes it would go face down, and go, and other times it would go on its side. And so what we did is we allowed an orientation constraint to be specified, so it would be land on face up or face down, because that affected the sound. So we could add extra constraints to the motion search. We also did an example with video where we could specify position constraints, so to look for motions that land here, and then go here, and then here, and here. And sort of, in a 2D land, becomes a sort of a direction constraint on the center mass. So then we could try to, make it go roughly where the video went. So anyway, we're still working on sound methods for animation, and I think there's a lot of challenges. I wish there were more people working on it, but I'd be happy to talk to anybody here about how to do sound synthesis better, especially when there's visuals involved. I think it's all really it's going to be challenging for computer animation to actually adopt this because they're so happy with post-production. There's not a huge incentive to change for them. But I think the future is rich for this area. Once we have methods, automatic methods for synthesis, and we have faster compute, then it's just going to be a no-brainer that people will just evaluate functions to simulate reality. And I think VR is going to be a huge application area because they really want immediate sensory feedback, and we have head tracking for HRTF. So I think that's going to be a big area. And better algorithms, lots of applications. Here's my son trying an Oculus Rift, and I asked him how it sounded afterwards, and he said, well, it sounds pretty bad, but the visuals are great, so I think people will be really excited about it when we have better sound. So anyway, so thanks for having me, and thank you for listening.
I'll say this. First of all, congratulations. Thanks for coming to Stanford.
Yeah,
Very much. So happy to have you. Yeah. What's available for mortals to actually get their hands on right now, like your modal analysis tools and things like that? How much is sort of usable outside of the lab?
Yeah, well, since I came here, a lot of my students have graduated, so it's hard for me to actually even do anything. I think one thing that we really strive to do is try to do all these different things, but now that we've done, one of this or that, we have a lot of different types of codes laying around, but we really want to try to get things in a state where we can do more sophisticated things, and that involves just building a better code base. We're hopefully off. I submitted a course to SIGGRAPH to help other people make some of these sound models, and one of the things we want to do is release some code so that other people can do it as well as just us. So yeah, currently there's not a whole lot. I mean, it's like you can read the paper, go implement it yourself kind of thing, but hopefully one way to make things have impact is to actually get code out there so it happens even when you're not around.
What are the ellipsoid modes known in closed form? Is that just something you have?
Yeah, they're not, in fact.
Okay.
It turns out that even like just a rectangular slab, the elastic modes are not known in closed form unless the body's like constrained on the side. But for like a free floating frame model, the modes are not closed, and so you have to analyze all of them. So we just did it.
I was also really interested in the fact that when you hit a couple of steel balls together, you're not hearing the modes.
Yeah.
That kind of surprised me. So I'm just wondering, what exactly are you hearing? I mean, in other words, would it work if the steel were completely rigid? If it were perfectly rigid, you would get exactly the same clicking sound?
Yeah, it's effectively acoustically and elastically compact. which is to say that the wavelengths are far longer than the dimension of the object. So effectively, it's perfectly rigid. If you had like some unobtainium balls and banged them together, they would sound exactly like, steel and so on. But the thing that's important though is you basically hear the time scale. So the elastic modulus is still important, not for vibration response of the surface, but because that determines the time scale of the contact force. So if you look at like a Hertz contact model, it's parameterized by the elasticity as well as the photon ratio and the mass density and the size of the bodies. And so you basically effectively hear the time scale of the impulse. So essentially like you hear the jerk of the motion. So you bang them together, you get an acceleration pulse like a half sine pulse. And then you take a derivative of that to get the sound. So it's a little smooth here. So you basically have a little hump, and you take a derivative of that, and you get some other pulse. And so you basically get this N wave pulse for a click, which is what you hear mostly. And the time scale of that click is based on the time scale associated with the contact force, which allows you to hear the difference between different materials. So even if your base frequencies are still high, you can tell the difference between a small glass ball or steel ball or a hard plastic ball based on their time scale. And you can play a game. We used to play this game in the car where my son would tease us and say, "And what am I shaking now?" He had a little change thing in the back seat, and he would take like a dime and 2 pennies and shake them together and say, "What's in my hands?" We're like, "Oh, it's dimes and pennies, damn it." So I can't use a quarter, a nickel, and it's like. And so you could hear maybe like a mode or two, but then you could also sometimes just tell by, something, the click would be a little different. And it's basically due to mass and stiffness and stuff. That surprises us too. I had no idea.
I don't want to monopolize, but one of the things that I've learned about post-production in movies is that they don't want the actual sound; they want something bigger than the actual. So when somebody's jaw gets hit by a fist, you're actually listening to a watermelon falling from the second floor, being recorded with a microphone 1 inch away. So, but you ought to be able to crank it up and go beyond reality and satisfy that.
So I think it's a tool that you can use to make all kinds of sounds. Whether or not you need the sophisticated physics and stuff when you have other sound synthesis tools, it's not really clear for a lot of those things where you don't want predictive tools or to be like necessarily 3D. It's unclear. I went and talked to Skywalker Sound, and I gave a talk there, and they thought I was a very strange person. But the thing that they seemed really interested in was like how to make voices, right? So how to make because their problem, Randy Tom told me that our problem isn't making bonks and bings and all these clanking sounds. Our problem is figuring out what this pixie or god or alien should sound like, and trying to make organic, natural sounding voices was a really struggle, hard thing for them to do. They try to take real sounds and play them forwards and backwards and mess with them, but they didn't like synthesis because it messes with things, as you know, it's hard to simulate voices. So yeah, that was their big problem. So they have all the time in the world to make up sounds. I guess like somebody like Ben Berg would probably be happy not to have added the 10,000th blaster sound to some soundtrack, and maybe that could be automated. I thought that places like ILM and Skywalker would be more interested in automated approaches, but they really are happy with post-production. They send the film to these guys, they add the sound, they don't have to tell them any signals for any events. But I think like video games definitely in VR care much more about automated approaches, whereas in movies, that's a 20th century art form in many ways.
First of all, that's a fantastic talk. Everything's awesome. But it seems like that there's a natural extension from this to scattering models, specifically things like, you have these ellipsoidal modalities, and you can go to ellipsoidal harmonics and start scattering a wave hitting, something like that.
Right.
Investigated any of that, or?
Yeah, so I was hoping somebody else would do that. Just because, Yeah, we really focused on sound sources, and that's kind of why we have all these, individual sound sources, ignoring everything else, and with the hope that it would go in as larger scattering engine. A lot of the oralization techniques are really geared at, larger environments, rooms, all this stuff. You look at like how to model sound in a cathedral where you have a lot of space and it's hard. Really, a lot of the things we care about are very near field kind of scattering events, which, when we did this stuff on trying to figure out how what sound a marble clacking together to do ball bearings because the model wasn't any good, we'd record this, and then we'd get the sound out, and just this complicated waveform. I'm like, what the hell is this? I thought it was supposed to be an N wave, and it's like this crazy. And then, which led to some bizarre, like 3 a.m. in the morning before the paper deadline with 2 guys trying to throw marbles so that they hit with nothing else around. Because we didn't have like a giant, so we have the microphone here, throw the ball like this. It was like, So, but then we got the click, and sure enough, it was an N wave. But all the other time, it was basically, we're imaging our hands and body and shoulders and heads. The thing that you actually hear is the scattering of that pulse off everything, and you get that. And if you don't have all that scattering, it doesn't quite sound right. It doesn't sound like a click. It's same like if you have a single drop falling in a tank of water, it doesn't have that scattering off in your field. It sounds like a fake digital bloop sound. But if you actually record it in a really good room with nothing else around, it actually sounds like that. But if you simulate it like that, people won't answer. So it's all this, I think a lot of the scattering and how far you're listening, the smell of the microphone, all that stuff really actually matters in getting the right effect. And we miss it all, so everything sounds dry and fake, but we don't have to do that. So I think in the future, ideally you can have some like Cornell box type scenario where you put everything in, animate it, and you render the light, and you render the sound, and all the scattering, everything is integrated and builds a coherent, consistent picture. I mean, very few people will want to do that, but if you build an automated tool to do that, you can. And I don't think it's as hard as simulating sound transport in a cathedral. It's just like, 1 meter cube of acoustic, volume isn't that at a time step. It's just a matter of connecting it all together.
Are they doing anything like this at Facebook for like the SDK for the Oculus Rift? Are they doing any kind of sound?
Yeah, so one of the people that is associated with our SIGGRAPH sound submission was from Ravish Mira from Oculus. And so they're interested in mostly like how, I don't know, so Oculus and Google are both really interested in like HRTF type modeling for head-mounted displays. Everybody wants to do that. And mostly they don't need anything that fancy, except that they want it to be personalized, because otherwise it's not very good. And they wanted to be able to do volume sources of sound, like if you have a waterfall or something. And so being able to capture and reproduce sound, so they want to do like 3D video or light fields and things like that. But they also want to have, record the incident sound field so you can move around and have it displayed properly. So they're interested in higher order animatronics and things like that. But mostly I think capture will be the thing that they really focus on, because that's the thing they can do well, and that's where the visual imagery and content will be. So when you have like a 3D YouTube channel that'll have that kind of audio encoded. As far as like simulating stuff in games, that'll come, but it's mainly a pain for the video game content creators, because they have they usually just like, you go into a room, they add like a stereo fill track, it was great. But now, you have to actually make it come from somewhere, because otherwise it doesn't make any sense. So it makes authoring things harder. So I think because of that, they'll want automated tools for doing it, so that you can, your physics engine will generate sound from a specific location. And that may actually be the reason why movie studios want to have better sound synthesis tools or different types of tools, just to get better spatialization. They talk about having so many channels, 24 channel stereo, but making that content is a real pain for audio engineers. So.
Has that happened in your work yet, that you rendered ambisonic position or something like that?
No, I mean, in principle it could be rendered, but we haven't really done it. We just rendered stuff to headphones. with some really bad HRTF. Yeah.
Yeah, well, now that YouTube's adopted Amazonic format,
Uh-huh.
it's kind of, yeah, that's recent. Pretty compelling, I guess. I mean, I'm not sure who's going to listen to it yet, but.
Right. Yeah, I don't know. But yeah, it'd be great to talk to people about any of these things. We're a bunch of like, physics dropouts, trying to do sound and stuff. Or just interesting to talk about more of that stuff.
Yeah, I guess what else, we really need to know what's coming up for courses that you might be offering and such.
Right, so I taught this like really small physics-based sound course in CS, which basically didn't was taken by like a handful of people. So it doesn't really fit into the CS curriculum because they don't do sound, and for the most part, and the animation people, it's just an oddity to them. So it's kind of like a weird niche area.
So Elliot was taking that course again.
Yeah, so I'm not doing a very good job of promoting it, I guess that's one problem. But yeah, so I think like there's probably, it'd be interesting to think about what kind of courses would be useful at Stanford in this area, especially as it develops. It's not really clear to me how it fits in. So I usually teach graphics courses and numerics courses and stuff like that. But
Well, this is a safe haven for you.
yeah, I know.
Oh,
Yeah. So that's great. Yeah, so if anybody's interested in talking, I'm pretty approachable. Just shoot me an email and I'd be happy to talk with you or have a coffee or something. So thanks for having me.